Hi, my name is Alusain Barry. Welcome to this lesson on applications of differentiation. Today we are in this lesson we are going to focus on solving a second example on applying the idea of rates of change. Okay, remember rates of change can be connected by the chain rule. Okay, so if we just state the chain rule, so according to the chain rule, if we are given a function y equals to something, okay, we'll be able to find the derivative of that function dy dx as we say dy du. If we assume y depends on our function u, which itself that u depends on another variable x. Okay, so now we can be able to find dy dx because you can imagine visually the u and the u cancelling themselves out. So we'll still be having dy dx. Okay, so this second example says the volume of a cube. Remember earlier we dealt with a sphere. Okay, the volume of a cube is increasing. Earlier it was decreasing, so the derivative dv dt was negative, but here it will be positive. Okay, because it is increasing. The volume of a cube is increasing at the rate of 2.5 centimeter cube per second, okay, at which the rate of change, okay, sorry, the rate of change, of the side when the side of the base when its length is 2 centimeters. Okay, that side, when the side of the base is 2 centimeters. Okay, now let's give ourselves some space so we can solve this problem. Okay, so let's see what we have here. First of all, let's say solution. Okay, now what we have been given in the question is the rate at which the volume is increasing with respect to time. Remember seconds, we have seconds here and this is centimeter cubed. So cubed is volume and second is time. So volume with respect to time. Okay, so this will be dv dt is what we have been given. You always focus on these units to direct you. Of course, it's explained in the question as well. Okay, so we have been given dv dt as 2.5 centimeters. Okay, so but which is just the same as 2.5. Right, now imagine a cube. Let's just draw our cube here. Imagine a cube. For a cube, all the sides are equal. Okay, of course I haven't drawn it to scale here because if here, for example, we have the height to be x centimeter, this base, the side of the base is also x centimeters. Okay, and this other side here should also be x centimeters. This is why the volume of a cube v is x cubed in this case. Okay, so we just multiply out the base, the side, and then the height. All right, x cubed. Now we have been given the rate at which the volume is increasing with respect to time. Now let's noting here the volume of a cube, since the volume of a cube v is equal to x cubed. Now, when we know, excuse me, the volume of the cube, we know now it depends on the side, okay, x. It depends on the side x. So now let us find the rate at which the volume changes with respect to changes in the side. This side, the side of one of the sides, okay. dv dx will be equal to, we are going to multiply the term by the power, which is 3, and then subtract 1 from it. So this will be 3x squared, okay, dv dx, the rate at which the volume is changing with respect to changes in the side x, right? Because now actually what the question asks us is to find the rate at which the rate of change of the side when its length is 2 centimeters. So we are looking for the rate at which the side is changing, okay? So that will be dx dt. But now let us go down a little bit. We have been given that dv dt is 2 centimeters. So we can actually say here, using the chain rule, we can say dv dt will be equal to, now let us say dv, let's express it in x, okay? dv dx, okay, dv dx multiplied by dx dt, right? Because what we are looking for is actually dx dt. If we cancel out, dx dx, we are still being left with dv dt, okay? Let's give ourselves some more space here. Okay, so now we already know dv dt, but we want dx dt. So what we can do, we can divide, sorry about that, let me wipe that. So dv dx, we are going to divide so that we are left with dx dt on one side, and then this also will mean we are going to divide here by dv dx. So this cancels out, so we are left with dx dt, dx dt, sorry, that was supposed to be t, dx dt is equal to, now we have dv dt here, which is now divided by dv dx, okay, dv dx. So now actually let's see what we have here. Let's see what we have here. We're going to have, so dx dt now, so dv dt, we know what dv dt is. dv dt, let's go up and see what we have, the rate at which is changing. This is 2.5, okay, so that's 2.5. Let's just write it down here. So we have 2.5 divided. If we're having divided, we can actually change this to multiplied by just saying 1 over dv dx, okay, by finding the reciprocal, right? So now this will be equal to 2.5 times dv dx. What is dv dx? The rate at which the volume is changing with respect to the side x. This is 3x squared. So 1 over 3x squared. Okay, so let's see. In fact, we note that let's come down here just so you note that we said earlier 2.5 is equal to 2.5. Don't forget. But remember, this is the same as 2 times 2 is 4. 4 plus 1, 5. 5 over 2. So we can just change this to the, in this fractional form. So we have 5 over 2 multiplied by 1 over 3x squared. So this is going to be 5 times 1, 5 over 2 times 3, 6x squared. Okay, so now we can just plug in x and find the rate at which the side is changing with respect to time. Okay, we'll have to move on to another video to complete this.